Have you ever felt like you're just, drowning in information, wishing there was a real shortcut to truly get a complex topic, to cut through all the noise, get straight to the core insights? Well, you're in exactly the right place. That's our mission here. Today, we're plunging into something really groundbreaking. How large language models, LLMs, are breaking free from what we once thought were, well, fundamental limits. They're evolving into general purpose problem solvers in ways that honestly feel a bit like science fiction. And it's all thanks to something called tool integrated reasoning, or TIR. Now, you probably think of LLMs as, incredible text generators, and they absolutely are, but this deep dive will reveal how they're making a profound shift, becoming something far more capable than just, say, sophisticated chatbots.
It really is a fundamental redefinition. We're not just talking about making them a little bit better at answering questions. This is about expanding what these models can even conceive of doing, pushing past a capability ceiling that once seemed, well, intrinsic. Imagine the implications, how we interact with AI, how it tackles scientific breakthroughs, maybe even how it thinks. It's all being reshaped.
And the sources for today are truly at the cutting edge. Our primary guide is the paper Understanding Tool Integrated Reasoning by Lin and Zhu from Tencent and Tsinghua University. This isn't just another research paper. It provides the first formal proof and a really deep, sort of mechanistic explanation for why TIR is so successful. We're also looking at some related fascinating research, too.
Yeah, and our mission today is basically to pull back the curtain on why and how tools make LLMs so much more capable. We want to reveal the surprising facts and the truly emergent cognitive patterns that are defining this new era of AI. We'll look at the theory behind it, the practical necessities, and the real-world results that clearly show LLMs are genuinely learning to think with tools.
Okay, so let's start with the baseline problem. LLMs are amazing at generating fluent text, answering complex questions. We see it every day. But our sources point out a consistent struggle. They falter when tasks demand super precise calculation, or, when they need to follow a really long multi-step search for a solution, or even when they need information that just wasn't part of their initial training data. It's almost like they hit an invisible wall. So what exactly is holding these pure text models back?
All right, this is where that concept of the invisible leash comes in. It's a term from some earlier theoretical work. Imagine a dog on a leash. It can explore within its boundaries, sure, but it just can't reach anything beyond that leash's length. Similarly, our sources explain that pure text LLMs, even with advanced techniques like reinforcement learning, RA-no-bone, they're largely confined to reweighting probabilities within their pre-existing knowledge. They can't discover fundamentally new reasoning pathways if those paths aren't already sort of there in their initial support or capability distribution. It's truly like trying to solve a puzzle with only the pieces you were given. If a crucial piece isn't in that initial box, you're just stuck, no matter how much you rearrange what you have. And the paper we're studying, it formalizes this. It notes that if a correct solution trajectory has a probability of 0, or effectively 0, in a pure text model's initial setup, then even massive amounts of reinforcement learning can never find it as a critical inherent constraint, a real hard limit.
Wow. Okay. And this is where it truly gets, well, mind-bending. The central thesis here is that tool integration fundamentally breaks this barrier. By introducing these deterministic, non-linguistic actions, things like calling a Python interpreter, LLMs, can now access solution paths that were previously impossible for them to even conceive of. It's like, as you said, giving that dog on the leash a pair of wire cutters. Suddenly the world opens up.
Exactly. And to help us visualize this, the paper uses an analogy. Imagine you need to find an impossibly specific piece of data, something truly unique, like a random string. A pure text model would have to just guess it, right? Like trying to find a needle in an infinite haystack. The probability of success is astronomically tiny, vanishingly small. But a tool-integrated model, it's like it can ask a trusted, all-knowing expert, the external tool, and get that exact piece of data instantly, deterministically. It's not guessing, it's knowing. It asks the tool provides. Simple as that. This shows that tools don't just help the LLM, they expand its fundamental capacity to generate correct problem-solving trajectories. They provide access to operations or information that were simply out of reach before.
Okay, so tools expand what's theoretically possible. That's a profound shift in what an LLM is, but our sources argue they're also a practical necessity. And it all comes down to something they call token efficiency.
Can you paint a picture of just how dramatically tools change what's possible within an LLM's limited working memory? Because that context window limit is always a factor. Absolutely. Think about an LLM's token budget. That's its context window. Basically, how much information it can hold and process at any given moment. The crucial insight here is that for any finite budget, There are algorithmic strategies that are simply impossible for a pure text model to express. Why? Because their natural language simulation would be intractably verbose. Just way too long.
Mhm.
The text required to simulate the steps of a complex algorithm would quickly, blow past the model's memory capacity. It just can't hold it all.
Yeah, I remember trying to explain a complex algorithm to someone who wasn't a programmer, and I just kept getting lost in the details myself. It's almost exactly what these LLMs face, isn't it? So, what does this token efficiency actually look like in practice? Give us a couple of compelling examples.
It's precisely that scenario. Imagine needing to check, say, a million numbers in a sequence. A pure text model would literally have to narrate each step. First, for N1, I check. Next, for N2, I check.
Hmm.
That scales linearly with the number of items. N, it floods its memory. Omega N, complexity in terms of tokens. A Python script for that same task. A few dozen tokens, maybe? A compact constant instruction?
Yeah.
O1, complexity. It's like the difference between writing out every single step of a long recipe versus just saying, bake the cake using standard procedure.
Huge difference.
Or take something like solving a massive matrix system in linear algebra. Trying to describe every single step of Gaussian elimination purely in natural language. For a big matrix, forget it. The text would be enormous, probably O n cubed tokens. It would exceed any reasonable context window. But with a Python tool, it's one compact, lightning-fast command, a single, numpy.lionelg.solve call, perhaps, O1, tokens, instantaneous comparatively.
Right, or dynamic programming like Fibonacci. That recursive explanation gets long fast too.
Exactly. Recounting each step, fib5, fib4 plus fib3, then expanding those. That leads to ON tokens again. A programmed recursive function, maybe with memoization. O1, tokens for the call itself. Same for graph search, like breadth first search. Describing it step by step in text is OV plus E tokens, the Python code O1.
So this token efficiency, it's not just a nice to have.
Not at all. It defines a model's feasible support. For any non-trivial algorithmic problem, there's a problem size beyond which the pure text representation simply exceeds any realistic token budget. Tools make these complex algorithms genuinely deployable. This means LLMs can now leverage the compact power of programming to solve problems that would be impossible to even describe in full natural language within their memory limits. It's about making complex reasoning practically accessible, not just theoretically possible.
The theoretical arguments are certainly compelling, showing us what could be. But the real proof, as they say, is in the pudding, isn't it? What did the numbers actually show when they put this to the test? What were the empirical results like?
Oh, the empirical results from the paper are, frankly, astonishing. The researchers ran experiments on really challenging mathematical benchmarks, like AIM and OmniMath, standardized tests, basically. Their pass-at-K analysis, which is a really robust measure of problem-solving potential, like how likely it is to get it right within cat tries, showed that tool-integrated reasoning models consistently and significantly outperformed pure text models. This wasn't just a slight edge. T elevated the entire capability curve. There was no trade-off observed, just a universal boost across the board. More problem solved, period.
Okay, elevating the whole curve. And when they looked at this flow of problem solvability on the OmniMath 512 dataset, how clear was the win for tier then?
Very clear. A really impressive 15.4% of problems that were previously unsolved by the pure text models were solved by the TIR models. That's huge. In contrast, only a tiny fraction, 1.8%, went the other way. Problems the pure text model solved, but TIR didn't. So that's a massive net gain in capability, something like 13.6 percentage points. It directly validates those theoretical arguments about expanding the feasible support. It just works better.
Now, it's natural to wonder, maybe cynically, couldn't this simply be about giving an LLM a fancy calculator for math problems? Like, of course, it's better if it can just compute things.
Yeah.
But our sources delve much deeper than that, right? They introduce this algorithmic friendliness metric, rating problems from 1 meaning abstract, non-computational, all the way to 5 meaning a direct algorithm application. What did that reveal? Was it just helping on the calculator problems?
That's exactly what they checked, and the result was really insightful. Even for problems rated as highly abstract, those with low algorithmic friendliness scores, like 1.0 to 2.5, meaning they require deep abstract insight rather than straightforward computation. Even on those, the TIR model still maintained a significant 9% performance advantage over the pure text baseline. This proves that TIR isn't just offloading simple arithmetic or acting as a glorified calculator. It's enabling the model to solve problems requiring deep abstract insight in fundamentally new ways. It suggests a far more sophisticated interaction with the tools than just, asking for 2 plus 2.
Okay, that is interesting. So if TIR isn't just a fancy calculator, how is the model actually leveraging these tools? The qualitative analysis, looking at how it solved things, revealed three emergent cognitive patterns, showing how it learns to think with tools. This is where we really start to see a new kind of intelligence at play, maybe. What's the first pattern they observed?
The first pattern is what they call insight to computation transformation. It's a really neat idea. Here, the model first engages in complex text-based reasoning. It thinks through the problem, conceptually, to distill it down into a form that can be solved programmatically. Then, and only then, does it use the code interpreter to execute a genuine algorithm with potentially complex control flow. Things like search, enumeration, dynamic programming, numerical methods. For example, they saw it tackle a complex geometry problem. The LLM first used its mathematical reasoning chops to derive a specific, tricky transcendental equation. Then it wrote Python code to intelligently search for solutions by iterating through a parameter space, using something like the intermediate value theorem to numerically detect where solutions might exist. This wasn't simple arithmetic. It was sophisticated algorithmic execution guided by prior abstract insight. The insight came first.
That makes perfect sense. It does the hard thinking, figures out the computable part, and then delegates the execution. Okay, what's the second pattern?
The second pattern is exploration and verification via code. This one's really cool too. For problems where there isn't an immediately obvious solution path, the LLM actually uses the code interpreter as an interactive sandbox, like a scratchpad. It generates hypotheses, writes short code snippets to test them out, observes the outcomes, and then iteratively refines its strategy based on what it learned. This is crucial for those problems requiring abstract insight, where you can't just jump to the answer. You have to feel your way there. For instance, in one complex number problem, the model started by trying a specific scenario, setting some variables to 1, calculated an initial value using its code interpreter, then used further code snippets to numerically explore other possibilities, building confidence in its hypothesis before attempting to construct a rigorous mathematical proof. It's like having a mini scientific lab right there within its reasoning process, testing, observing, refining.
That's incredible. It's almost like it's prototyping its solutions using the tools, probing the problem space. Okay, and finally, what's the third key way these models are learning to use tools?
And the third pattern is offloading complex calculation. This is maybe the most obvious use, but it's still incredibly vital. The model simply delegates tedious or error-prone calculations to the interpreter, things it could try to do in text but would likely mess up. This minimizes those unforced computational errors that can easily derail a long chain of thought, especially in math or physics problems. For example, a geometry problem might involve really intricate vector math or algebraic manipulations. The LLM performs the high-level reasoning, sets up the calculation, and then precisely executes these numerical steps in Python to avoid manual mistakes. It's about maintaining the integrity and reliability of its reasoning, offloading the grunt work to where it's most efficient and accurate.
Makes sense. Focus on the strategy, let the tool handle the number crunching.
Right. And what's truly profound here, as the paper points out, is that the first two patterns, insight to computation and exploration verification, they represent entirely new computational equivalence classes. This means these models are developing fundamentally different ways of thinking and solving problems than pure text models could ever achieve. These strategies were either impossible or just intractably verbose before. They're not just using tools, they're genuinely thinking differently because of them, opening up entirely new conceptual approaches to problem solving.
Okay, so if using these tools is so beneficial, how do you actually get an LLM to use them more effectively? For instance, to bring in its code interpreter earlier in its reasoning process, maybe for that exploration phase, rather than just using it as a last resort calculator. It turns out traditional methods like reward shaping, giving it an extra reward for calling code early, can actually destabilize the whole training process. That feels really counterintuitive. Why would that happen?
It does seem strange at first glance. And the paper explains a critical flaw they identified. With some typical reinforcement learning algorithms like PPO, rewards get normalized within batches of data during training. The problem was, if a model consistently got answers right using late code calls, the normalization process could inadvertently cancel out the reward signal for correctness itself within that batch. This meant the only signal left with any variance was the auxiliary reward for early code use. If a correct solution used code late, it might get a lower score than an incorrect solution that happened to use code early. So the model could actually be punished for doing things right if its code invocation wasn't early enough, a frustrating and counterproductive mess. It's like a bonus system that accidentally penalizes your best workers because everyone in their group is performing well.
Wow, okay, that's a subtle but dangerous trap, so how do they fix it?
To get around this, the researchers developed a really clever solution called Advantage Shaping Policy Optimization, or ASPO. Instead of messing with the reward function itself, which caused the instability, ASPO directly modifies the advantage function. The advantage function is essentially the internal scorecard that tells the model how much better one action is expected to be compared to the average action in that state. ASPO calculates the advantage based on correctness first, and then it adds a stable, controllable bias to that advantage calculation, specifically for actions involving early tool use. It shapes the advantage, not the raw reward.
Ah, so it guides the learning without messing up the fundamental signal of whether the answer was right or wrong. And the results were remarkable, weren't they?
Absolutely. ASPO maintained training stability and task performance, unlike the naive reward shaping approach, which, they showed, quickly became unstable and degraded performance. And it dramatically shifted behavior, just as intended. The average position of the first code call in the model's reasoning moved significantly earlier, from around 4,000 tokens down to just 1,000 tokens into the response. And the number of code rounds, how many times it called the tool, more than doubled. Crucially, this was achieved without reward hacking. The model wasn't just inserting useless print hello calls early on to game the system. The change reflected a genuine shift towards a more interactive and iterative problem-solving style using the tool.
That's fantastic. More tool use earlier and without breaking things.
Exactly. And you can even fine-tune how aggressive this behavioral shift is with hyperparameters in ASPO. This means we now have a robust framework for guiding LM behavior towards desired styles like early, exploratory tool use, without compromising accuracy or training stability. It's a precise way to shape how these powerful models interact with their external capabilities, letting us tailor their problem-solving approach more effectively.
So, as we wrap up this deep dive into understanding tool integrated reasoning, for me, what truly stands out is how this work fundamentally redefines what we thought an LLM was capable of. They are no longer confined by that invisible leash of purely text based reasoning. Seems obvious now, maybe, but the proof is powerful. They're expanding their capabilities through deterministic tool use, overcoming those token budget limitations with incredible efficiency, and demonstrating genuinely new cognitive patterns like that insight to computation transformation and the exploration via code. It really feels like a paradigm shift.
Indeed, it fundamentally shifts our perspective. LLMs aren't just monolithic problem solvers anymore. They are increasingly becoming reasoning engines that intelligently delegate tasks to specialized tools. And as the paper notes, I think in its appendix, this principle extends far beyond just Python interpreters. Think search engines, verifiers, external memory systems, maybe even interaction with robots in embodied environments. We're witnessing the dawn of truly agentic AI, where these models can dynamically adapt their problem-solving strategies using a whole suite of external capabilities. It's not just one model anymore.
A network of capabilities orchestrated by the LLM.
Precisely. And that leaves us with a truly exciting vision and maybe a provocative thought for you, the listener. If AI models are learning to think with tools in ways that were previously impossible for them, fundamentally changing how they reason, what does that mean for the kinds of problems we can tackle with AI in the future? What new frontiers does this open up? And how might this ability to dynamically adapt its reasoning strategy to integrate external deterministic functions fundamentally change the nature of AI intelligence itself? It's a question that really makes you think about what's coming next.